Hello, my name is Roberto, and today I would like to show you a short tutorial on how to run TD-DFT calculations with Psi4. So I will be working through this notebook mostly, and this is running on my binder, and you can find my binder at this URL, and the corresponding Git repository is also available, and you can have a look at the resources there if you have more questions. Okay, so let's start by saying that Psi4 1.4 will enable you to run TD SCF calculations, so response calculations at the Hartree-Fock and DFT levels with the range of functionals. This new feature, the first thing that I would like to do is to give credit to the people that work towards landing this important feature in Psi4. So you will be able to run these calculations either using the random phase approximation, RPA, and that is work mostly by Andrew James and Diane Smith. You will also be able to use the Tam-Dankov approximation, or TDA, and that is work mostly by Rui da Cunha. And this functionality is available from Python input files, and that is worked by Jeff Schreiber and Laurie Burns. Or you can write Python scripts and use Psi API to access TD-DFT. And this is again work mostly by Andrew James and with some additions by me. And also TD-DFT calculations can be run including Solvent effects, either through the polarizable continuum model, PCM, or polarizable embedding, PE. And these are contributions from Holger Kruse and Maximilian Scheurer. And finally, the data can be plotted. So you can get spectra out of the raw data that comes from Psi4, not only as sticks, but also with a convolution with empirical line shapes. So including an empirical lifetime for the excited states, so to speak. Okay, let's first look at how you can access this functionality through Python. Okay, as I said, the bridge between the functionality itself, the code, and the Python user-facing input files was built by Jeff Schreiber and Laurie Burns. And there are two styles in which you can invoke a TD SCF calculations. One uses the energy driver. So you would specify energy function, and then the usual function, for example PB0, prefix with the TD dash for time dependent, and then slash and the basis set of your choice. And this will first run the reference state calculation using PB0, and then the excited state calculation. Okay, so all the settings for the reference state will be automatically inherited by the excited state calculation in this way. Another way is to use again the energy function, but instead of prefixing the functional name with TD dash, you would ask to return the wave function object. So once you have the wave function object, you can then call the TD-SCF method, passing this wave function object, and the excited state calculation would be then run on top of the reference state. So there are a number of new options, of course, for this new functionality. So, for example, we need to state a number of routes or states for which to run this calculation, the number of states to target, and whether we want to use RPA, which is the default, or Tam-Dankov approximation TDA. And this can be done with a set command to set the options, and these are not the only options that you can use to control TD-SCF calculation. There are more related, for example, to the convergence thresholds and the number of iterations in the response solver, and these you can look at in the manual. So a complete input for example, for the methyloxyren molecule, would look something like this, where you specify the molecule as usual. You can set the number of threads, and then you would give, as I said, the number of states, 10 in this case, and whether to run TDA or RPA, in this case TDA, and then in this case we use the energy driver with the TD dash prefix to the name of the function. This can be run as usual. Sorry for that. This can be run as usual. So we would call Psi4 minus input moxie.imp, which is the name of the file, minus o moxie.dat, and this would run the calculation in the background for us at the moment. Okay, while this is running, let's look at the final results, which I have copy-pasted here in the notebook already. So the final results will report the number of states. So we asked for 10 states, so here they are, and the characterization of these excited states. We ran in C1, so this molecule has no symmetry. So the characterization is not extremely helpful because these are singlet states, so that's why there's the one. And the transition, and both the ground state and excited state are in the irreducible representation A. So this doesn't really help us, but we can characterize, of course, the excited states by increasing energy, which is what we're doing here. So it's reported in atomic units and in electron volts, and we have the total energy, which is the ground state energy, plus the excitation energy, of course. And then we have some observables. So the oscillator strand, both in the length and velocity gauges, and the rotatory strand, again, both in the length and velocity gauge. There is a big warning that is printed out at the moment on top of this final report, and this is because we are not using London orbitals yet. So the length gauge rotatory strands are not gauge origin invariant. So for example, if we change the origin of the gauge by translating the molecule, we will get different results here. Now that we've looked at the final results, let's also look at what gets printed slightly before. And here we have a list of the options that were set for the solver. So the threshold for convergence is set to 10 to the minus 4. The threshold for convergence is based on the convergence threshold for the RMS on the density in the SCF, so that we're sure that we never try to converge the excited states tighter than the reference. The reference is RHF. Again, this is a closed shell molecule. And then we are asked for Tam-Dankov TDA, and this means that we use a Davidson solver. Then we have a report of how many roots we asked and in what symmetry, and the iterations of the solver. And this is a subspace solver, so we will expand our solution in a certain number of trial vectors. And this number of vectors impacts how much memory the solver will use, and this is reported here, how many vectors we are using at each iteration. Whenever the number of vectors exceeds this maximum number of expansion vectors, the subspace will be collapsed, and there will be an implicit restart of the iterations. Okay, so this is how it looks if we use Python. As I said, we can also use this functionality through Psi API. The relevant function is called TDDFT_excitations, and this can be found under the driver. So we would do import Psi4, and then from psi4.driver.procrouting.response.scf_response, we would import this function. And then it proceeds mostly as usual. So we declare the geometry, and we have to set these options, say JK, to true. This has to be done explicitly. It's not implicitly done for us in Psi API. Now, in this case, I want to run an Hartree-Fock calculation in CCBV-VDC with this MOXIE molecule. And again, I ask for, sorry for that, for 10 states. So this calculation, again, I can run, and this will take a little bit. As you can see, this function, TDDFT excitations, returns a variable that I've called res for result, and this contains all the results from a TD-SCF calculation that we saw printed in the output. So if we look at the output file moxie.out from this calculation, we will see a report that is exactly similar. Note that in this case we're using RPA, the random phase approximation. So rather than using a Davidson solver, we will use what we call the Hamiltonian solver. There's more details on that later. So what's in this result variable? So this is a list with as many elements as roots that were requested. So in this case, it will have 10 elements, and each of these elements is a dictionary. And this dictionary contains everything that has been calculated for the given root. So if I print it out, I get the excitation energy, the transition properties, so electric dipole transition moment in the length gauge, the oscillator strength in the length gauge, and then the same in the velocity gauge, the magnetic dipole transition moment, rotatory strands in length and velocity gauges, the symmetry, spin symmetry, and also the left and right eigenvectors for the alpha and beta spin. And these are Psi4 matrices. And now we will look at that a little bit more soon. So there are some known limitations to our implementation at this point. So for example, if you try to use symmetry with density fitted to electron integrals, the code will crash. So this is probably a bug that needs to be fixed. Excited states of triplet symmetry cannot be computed from a restricted DFT reference at the moment. And this has something to do with the spin adaptation in the DFT functionals. And excited states from an unrestricted reference at the moment only work for R3FOC and LDA. And this has also to do with the spin adaptation in the case of unrestricted references for functions other than LDA. Okay, let's look a little bit at what happens behind the curtains when we run these kind of calculations. So we're doing a response calculation. So basically we're trying to solve the time-dependent Schrödinger equation when we have a time-dependent perturbation that we assume to be periodic. So in this case, for example, an electromagnetic field with a certain frequency and superposition of monochromatic waves that all share the same fundamental frequency. So rather than solve for the actual wave function, this 0 of t here in the Schrödinger equation, we want to look at observables, so at expectation values, and we expand this time-dependent expectation value in terms of the frequency components of the perturbation Vt. And then all these components here, these are Fourier components because they are frequency dependent, and these are called response functions. So of course, this expansion does not truncate in any low order, so there are many orders to which we will have contributions to this time-dependent expectation value, but studying the response functions to lowest order will give us access to most properties that we can explore experimentally through spectroscopy. So a response function can be expressed as a sum over states, as I've done here. And these omega ij, they're the excitation energies of the system, also called the poles. And the value of the response function at the poles are called residues, and they are the transition properties. So these matrix elements of the A and B operators at the numerator. A sum over state expression requires that we have access to the whole eigenbasis of the Hamiltonian, which we never have. So instead of trying to form the sum over state expression, we can target directly the response functions in an indirect manner by diagonalizing the molecular electronic Hessian. So in self-consistent field theories, this problem looks like this, where we have the molecular electronic Hessian, the response vector, the excitation energy, and then this metric matrix. Okay, so the A and B matrices that appear in the molecular electronic Hessian are given in terms of Fock matrices and two electron integrals. And in case we have we use the DFT, there's an exchange correlation contribution. So this whole matrix has size O times V squared, where O is the number of occupied orbitals and V is the number of virtual orbitals. So we cannot form this thing explicitly for large molecules, or even for small molecules if we want to target a lot of states. So what we do is we expand this vector in a set of so-called trial vectors, so in a subspace that we can build incrementally, and then solve the projected problem in this subspace by direct diagonalization. Then at every iteration we check whether we reach convergence in the norm of the error vector, and if not, we enlarge the subspace until we ideally reach convergence. So the key point for efficiency to this kind of algorithm is being able to form the first half projection. So basically the product between the matrix and a trial vector. Okay, so this is also called forming the sigma vector. And if we have efficient matrix vector product functions, then this can be done rather efficiently. Another problem is that even though the whole molecular Hessian is Hermitian, the problem here is not an Hermitian eigenvalue problem. It's a generalized eigenvalue problem because we have this non-unit metric matrix. What we can do, however, is recognize that this has a different symmetry, what is called Hamiltonian symmetry, such that the roots appear in pairs omega n and minus omega n. And also the eigenvectors are paired. So if we use this symmetry, which is equivalent to doing a block diagonalization, we end up with this problem of reduced dimensionality, which you can further transform by introducing this vector Tn to something that is Hermitian. So this whole matrix here now is Hermitian, and we can use an Hermitian eigenvalue solver. The thing that we need to note, however, is that this is valid if and only if the SCF reference is stable, that is, if the A minus B matrix is positive definite, because otherwise we cannot form the square root of it. Okay, now the Tn here is the xn plus yn linear combination, which is the right eigenvector. But we also have the xn minus yn linear combination, which will be the left eigenvector. So now, since the original problem was non-Hermitian, we have a set of right and a set of left eigenvectors, which are bi-orthonormal. So that is an important condition for the algorithm. In the Tam-Dankov approximation, we only deal with the A block, which is Hermitian by itself, and hence we can use a Davidson solver that works really well for subspace iterations of for Hermitian eigenproblems. Okay, now that we have the excited states and the left and right eigenvectors, we only have part of the story, because if we want to study excited states, we not only have to know where they are located, so the excitation energies, but also if they are accessible from the ground state, so whether the excitation is allowed, so it's a bright state, or not allowed, so a dark state. To do that, we need to look at observables, in this case transition properties between the ground state and the excited state, and that we can evaluate with oscillator strengths, for example, in the case of one photon absorption spectra. So these quantities, in this case, this is the oscillator strength in the length gauge. These are calculated already by Psi4 whenever the solver converges. And together with this, we calculate a lot of other properties. So this is also magnetic transition dipole moments and so on. But it is quite easy to re-implement the calculation of these quantities, given that we store the left and right eigenvectors in the result list that comes out of the solver. So here you see this is such an implementation. So the thing that we do is get a means object, and from that means object we get, for example, the dipole moment integrals in the length representation, and we just need to get the occupied virtual block to compute the oscillator strength. And then once we have that, we take the right eigenvector and do an inner product with each integral for each Cartesian direction. And then once we have that vector, we can calculate its norm and combine it with the excitation energies and calculate the oscillator strength. And here I'm just checking that the stuff that we have calculated matches with what was calculated by Psi4 itself. Okay, as I said at the beginning, on top of this, we can also we also provide functions for fitting with empirical line shapes, so that you can get nice spectral plot that can be compared with experiment. So Psi4 doesn't do the plotting by itself, and this is a choice that I made so that we do not entangle Psi4 with any specific plotting library, and so that the user has the freedom to run whatever visualization pipeline they might like. So what Psi4 provides is a function called spectrum that will take a list of the poles, so the excitation energies and the residues. They can be rotatory strength or oscillator strengths, and then does the fitting with a Gaussian line shape or Lorentzian light chain, and with a given gamma, with a given finite lifetime. So this function can do a few things. You can decide which kind of output unit measure you want for the x-axis, nanometers, atomic units, electron volts, and so on. But the y-axis will always be in macroscopic absorbance units, both for one photon absorption, OPA, and electronic circular dichroism, ECD. So let's have a look how you might do that. Okay, so from our result list, we create another list that only contains the excitation energies in atomic units. And we collect the residues for OPA, one photon absorption, which are the electric dipole transition moment in the length gauge. And for ECD, we take the rotatory strength in the length gauge. Okay, once we have this, we give it to the spectrum function, and this returns a dictionary of dictionaries. Okay, so it's a dictionary of dictionaries because you might want to either plot the convolution or the stick spectrum or both. But in any case, if you want to use a unit different from atomic units for the x-axis, it needs to run the transformation of units for you and adjust the y-axis so that it's reported in the macroscopic units that are used in experiment. So for example, if we look at the sticks key in the dictionary, you will see that now it's transformed to nanometers, the poles. It's not atomic units anymore. Okay, and then we can plot this. In this case, I've chosen to use Altair, the Altair library. And this will give us a plot. Yes. So this is our one photon absorption spectrum up here with the sticks and the convolution with the Gaussian broadening. And this is the ECD spectrum. Very nice. So the last thing that I want to show you is that you can do the same including Solvent. Okay, now I'm using Psi API again, and I'm doing it for a smaller molecule, hydrogen peroxide, and I'm using PCM. So I ask for 10 roots again. There's nothing different in the calculation itself apart from the fact that I'm setting PCM string, the input, and I'm asking to run a PCM calculation. So in a PCM calculation, one needs to take care for excited states of running with what is called non-equilibrium solvation, meaning that the excited state will not be in equilibrium with the solvent distribution with which the ground state has been optimized. So we need to take care, we need to take into account this difference in the environment that the excited state density feels with respect to the ground state. So this calculation takes a little bit. Now it's done, and now exactly as before, we can plot the results. And these are again the one photon absorption and ECD spectra for hydrogen peroxide with a Gaussian broadening. And with this, I thank you for your attention, and I hope that you will find this useful, both this tutorial and most especially TD-DFT in Psi4. Thank you.